Okay, let us talk about two phase Poissony flow. Okay, here we talk about two fluids between two infinitely long parallel plates, and the two fluids have different viscosities. Okay, so we would achieve an interface between the two fluids which is flat. So the Young Laplace pressure drop would not exist. Okay, and we would have the interface between the two plates at some height h star. Okay. So with that let us look at the sketch. So we talk about two phase Poissony flow. Okay. So here we talk about two parallel plates. Let us say this is x and this is z, this height is h, and we have, let us say this is the interface, okay, at h star. Okay. So here we have the P0 at the inlet will be P star plus delta P, and here we have P L will be equal to P star, this is L. Okay. So this fluid has viscosity eta 1, and this fluid has a different viscosity, this is eta 2. Okay. So here we have two fluids viscosity eta 1 and eta 2, and we have a flat interface at z equal to h star. Okay. And since the interface is flat, our Young Laplace pressure is going to vanish. So this is 0. So the pressure field is similar to single phase Poissony flow. That means it varies linearly. Okay. So Px could be P star plus 1 minus x over L into delta P. So that is how the pressure is going to vary between the inlet and outlet. So as I said, there are two fluid layers. For the bottom layer is between 0 less than z less than h star, and the top fluid layer is between h star less than z less than h. Okay. So in the two domains the velocities we can write, so uz equal to u1 z when 0 is less than z less than h star, and it is u2 z when h star less than z less than h. Okay. So we can satisfy the no slip boundary condition. Our no slip boundary conditions are u2 at we are in this case we are taking eta 1 and eta 2. So u1 u u1 at z equal to 0 is going to be 0 and u2 at z equal to h is going to be 0. So, those are no slip conditions. Now, we can generalize the expression for the velocity that we have derived for single phase fluid between two infinite parallel plates, and we can apply it to this situation for two different fluids. Okay. So, if you do that, for single phase fluid between infinite parallel plates, we know the velocity expression. So, uz is going to be delta p over 2 eta L into h minus z into z. So, this satisfies the boundary conditions at the top and bottom all, assuming there is a single phase fluid. Okay. So, in this case, if you generalize, what we would get is we can write u1 z equal to delta p over 2 eta 1 L. So, the delta p and L, they are the same for both the fluids, okay, into h1 minus z into z. Okay. So, this will satisfy the boundary condition u1 at 0 equal to 0. Okay. So, for the velocity u2, we can write u2z is going to be delta p over 2 eta 2 L into h minus z into z minus h2. So, this will also satisfy the boundary condition u2 h equal to 0. Okay. So, now you can see here there are two constants we have introduced, okay, h1 and h2, h1 h2, they are constants, and these constants could be determined using the boundary conditions. So, now in addition to these no slip boundary conditions, we have additional boundary conditions coming at the interface. Okay. At the interface between the two fluids, we would have additional boundary conditions coming in. The one boundary condition at the interface would be that the velocity of the two fluids will be equal at the interface, and the second boundary condition is that the shear stress will be equal. Okay. So, eta 1 into the velocity gradient will be eta 2 into the velocity gradient for the other fluid. Okay. So, if you do not satisfy the shear stress continuity boundary condition, then there will be on physical forces that might be present at the interface. Okay. So, we would have boundary conditions at the interface. So, one would be the velocity u1 h star will be equal to u2 h star. Okay. So, this is velocity continuity boundary condition, and the other one is shear stress continuity. So, eta 1 into del u1 over del z equal to eta 2 into del u2 over del z, and this will be evaluated at h star is at h star. Okay. So, using these two boundary conditions, we can apply these two boundary conditions to this equation here, okay, these equations for the velocity field, and if you do that, what you will get is we will evaluate the two constants. So, we can find that h1 will be equal to h plus h2, where h2 will be given by this expression eta 1 divided by eta 2 minus 1 into 1 minus h star divided by h into so divided by eta 1 by eta 2 into 1 minus h star over h into plus h star divided by h into h star. So, we get an expression for the two constants h1 and h2, okay, which can be used in the expression for the velocity here. Okay. So, you would have the expression for u1z as well as u2z. Okay. So, if you plot that, if you plot how the velocity would look like, here it would be increasing parabolically, and here there will be a discontinuity in the velocity profile where the gradients are going to be different. So, the slope of the profile is going to change here. Okay. So, these are the velocity profile, and you can see that there is a change in the slope that is occurring at the interface between the two fluids, and this change in slope is because of the equal shear stress requirement, and given that the viscosities are different. Okay. So, two fluids in microchannels has practical importance in applications, for example, in case of flow cytometers, where we need to focus a sample fluid using a sheath fluid, and there our goal would be to bring down the width of the sample stream to a size equal to the size of the particles that we want to detect. So, the particles should move single file. So, in that case we were talking about a case similar to what we discussed. Okay, we would be having two different fluids of different viscosities, and we can perform analysis similar to what we just did to determine at a particular flow rate what would be the width of the sample stream. Okay. So, with that, let us move on and discuss time dependent flow, where the velocity will be a function of time. We will consider a simple case of a Couette flow, where at time t equal to 0 both the plates will be stationary, and we will have a fluid at rest in between the plates, and for time t greater than 0 one of the plates would start moving, and when it starts moving, how the velocity of the fluid is going to change with time. And we know at steady state in Couette flow the velocity profile will be linear, but we are interested in the time domain where the flow is still in the transient range between 0 to some time t before it gets fully developed. Okay. So, let us talk about time dependent Couette flow. So, here we have one of the plates, let us say this is the bottom plate, this is x direction, and this is z direction, and this is the second plate, both are of same length, let us call it L, and this moves at a velocity u0 for t greater than 0. Okay, and this is u h 0 is 0, this is no slip boundary condition, so will always be satisfied on the top wall, and same is the case on the bottom wall, u 0 t will be 0. Okay. So, this is at time equal t equal to 0, this is at stationary, but at that time at some finite time this is going to move. Okay. So, this is only valid at time t equal to 0, but this plate is stationary. So, at all times this is going to satisfy the no slip boundary condition. We consider G in this direction, and this is h is the separation distance between the plates. So, we can write that u h t. So, the velocity of the upper plate here equal to 0 for t less than 0, and it is going to be u0 for t greater than 0. So, that is the situation we are talking about. So, and here similar to the Poissony flow, we can write u is a function of z and time. Okay. So, what it means is that the velocity along y direction and velocity along z direction, they are 0, and we have only x velocity which is a function of z and t. So, we can write the Navier-Stokes equation for this simplified case. Here we can write del square u, which is a function of z and t, over del z square into eta, thus the viscous term will be equal to rho into del u over del t. So, that is the unsteady term. So, this is the equation which is relevant here. So, this is the unsteady term, this is the viscous term. So, for t greater than 0, we can write the boundary conditions and initial as well as final conditions. Final condition will be the steady state conditions. So, the boundary conditions can be written as u 0 t will be 0 and u h t will be u 0. So, the velocity of the top wall is going to be u 0. So, that is the velocity of the top wall, and the bottom wall is at rest. So, this is going to be 0. The initial condition is going to be u z time equal to 0 is going to be 0, and the final condition when time is infinite, u z infinite is going to be u 0 into z over h. Okay. So, that is how when time t equal to infinity, the velocity is going to vary in this fashion. Okay. So, linearly varying with z. Okay. So, this equation is a linear partial differential equation, linear second order partial differential equation, which can be solved by Eigen expansion. So, here in the velocity term, we have velocity has two variables, one is z and the other is time. Okay. So, by Eigen expansion we would be able to separate the velocity field, which is a function of z and t, to two different variables, okay, two different functions with single variable. We will have u n z and time t n t. Okay. So, if you do that, so this is a linear partial differential equation second order that we are talking about. Okay. This is the second order linear partial differential equation, and to solve that we would use method of Eigen expansion, where u z t will be expressed as un z and t n t. Okay. So, it will be the velocity field which is dependent on two different variables will be converted as the product of two variables with two functions with single variables, okay, z and t separately. So, if you do that, we can write the solution u z t in terms of Fourier expansion. We can write this u z infinity. So, this is the steady state solution, okay. This is the steady state solution minus n C n into u n z t n t, okay, which we can also write as u 0 into z over h. This is the steady state solution, okay, what we see here, right, minus summation n C n u n z t n t, okay. So, this is the our expected solution using Fourier the Eigen expansion, okay. So, this is the steady state solution. What it means that the expansion here the same here, it will vanish when t equal to infinity. So, these terms, the expansion term will be equal to 0 as t tends to infinity, then only we will have only these solutions, okay. So, so eigen function, eigen expansion must vanish as t tends to infinity, and also when you are talking about z equal to 0, okay, when you are talking about z equal to 0, this function should be 0, okay, and when we are talking about z equal to h, okay, this function is going to be the at time t equal to 0 is going to be 0, at time t greater than 0 is going to be u 0, okay. So, this expansion is going to vanish also for time t equal to 0. So, z will be 0. So, this term will be 0, okay, and for z equal to h, this term is going to be u 0, okay. So, the expansion term must also vanish for z equal to 0 and z equal to h. So, then only the boundary conditions and the final conditions will be valid to satisfy boundary conditions and final condition, that means steady state condition, okay. So, now if we substitute this the Eigen expansion in this equation here, what we get is this, we get an expression t n t into del square u n z over del z square will be equal to, so you here you would have nu the eta over rho, so that will be 1 over nu, the kinematic viscosity 1 over nu into u n z into del t n t over del t, okay. So, we can also write this as, let us separate the variables divided by del square u n z over del z square divided by u n z, okay, will be equal to 1 over nu into del t n over del t divided by Tn T. Okay. So, here if we look at this expression, the left hand side is a function which is dependent on z, the right hand side is a function of t, and these two expressions can be equal only if these two are equal to a constant. Okay. So, we can they will be equal only if they are equal to a constant, and we call this constant as lambda n. Okay. So, lambda n minus lambda n is a constant. Okay. So, in that case we would have 1 over un z into del square un z over del z square equal to minus lambda n, and that will also be equal to 1 over nu del Tn T over del T into 1 over Tn T. Okay. So, this can be solved, right, this can be solved easily. So, we can find the solutions. The solutions can be un z is going to look like this, sine of square root of lambda n into z, and the Tn T is going to look like e to the power minus lambda n into t, because this is first order and this is second order. So, this is how the equation, the solutions are for un z and Tn T will look like. Now, if you want to determine lambda n, how do we determine lambda n? We have to use the conditions Tn infinity is going to be 0. So, when time tends to infinity, this Tn term is going to vanish. So, if that is going to vanish from here, you can see that lambda n has to be positive. Okay. Lambda n must be positive. Okay. So, this is something we are talking that about steady state. So, in that case, if Tn infinity will be 0 as t tends to infinity, this is only possible when lambda n is positive. So, lambda n must be positive. So, lambda n is greater than 0, right. Now, we have additional conditions. We have un 0 equal to un h, which is 0, okay, and this is no slip condition, right, un h, right. So, from there if you look at this equation here, what do we see here? We see that lambda n, square root of lambda n must be n pi over h. Okay. So, only if square root of lambda n will be n pi over h, this term will go to 0, satisfying this condition here. Okay. So, n here is 1, 2, 3, okay, up to n. Now, to determine, now we have determined lambda n. Now, let us try to determine what is this expansion constant is going to look like. Okay. So, the Eigen expansion constant Cn to be determined, and to do that use u z 0 is going to be 0, right. When time equal to 0, this is 0. So, Tn 0 is going to be 1. Okay. So, Tn 0 will be 1. right. So, Tn0 is this expression, right, here Tn0 will be 1. Why Tn0 will be 1? Because when t equal to 0 this term is going to be 1, right. So, Tn0 will be 1 when t equal to 0. So, what we get from here? We get n equal to 1 to infinity Cn sin n pi z over h, okay. This term here Cn into even z, this is becoming 1, t and t is becoming 1. So, we are talking about this term n equal to 1 to infinity. This term is going to be our nothing but u z infinity, okay, because this is 0. So, if this is 0, this you can take it to the other side of the equal sign. So, this is u z infinity or u naught into z over h, okay. This is what you will get. Now, from here you can get Cn and substitute in the velocity field equation, and if you do that you can get Cn here, and if you substitute in the velocity field equation you get z u z t equal to u0 into z over h minus 2 by pi summation n equal to 1 to infinity 1 over n minus 1 to the power n plus 1 into sin n pi z over h, okay, into there is an exponential term which will be multiplied here. This is you know, so this is exponential minus n square pi square into nu over h square into t, okay. So, this is going to be the expression for the velocity field when we are talking about transient state, okay. And as you see here, this is an exponential term which decays quickly as n increases, okay. And the best value of n for which this will have some quantity is n equal to 1, because we said that n varies from 1 to n here, okay. So, we can say that for n equal to 1 the value can be the best value, okay, and n as n increases it is going to decay very fast, okay. That is what we see from this equation. So, if we put n equal to 1, then you can write u z t will be equal to u0 into z over h minus 2 by pi into sin pi z over h into exponential minus pi square into nu over h square into t, okay. So, this is the expression when n equal to 1. For n greater than 1, this this value again will be very negligible, okay. So, we just evaluate for n equal to 1. So, here if you look at this term, we can define a characteristic time scale okay. Let us call it tau, that will be h square divided by pi square nu, okay. So, as t increases and it becomes t is let us say some n times tau, then we get steady state. Okay. So, what it means is that as the characteristic time constant is small, we obtain the steady state very quickly. Okay. So, if you are talking about a quiet flow situation where the height between the two plates is small or the kinematic viscosity is very high, the steady state will be attained very quickly. Okay. So, if you look at the profile, how it is going to vary with time. So, we are going to draw at various time steps. So, let us say at time equal to t1, it is going to start something like this. Okay. So, this plate is moving, right. So, it will move something like this, and time t equal to t2, this is going to bend little further, and this is time t equal to t2, and this is time t equal to t3, right. And when we have t equal to Tn, okay, a large time step, which is depending on the characteristic constant, we would have a flat velocity profile. Okay. So, if we superimpose all these on a single plot, this is how it is going to look like. What will happen is, initially it is going to be something like this, then it will be like this, then like this, and then finally it is going to be linear. Okay. So, this is as time increases. Okay. So, with that, let us move on and talk about slip flow in case of microchannel flows. So, we will consider quiet flow situation where we will talk about the liquid the fluid to be gas. Okay. We know that in case of liquid flows, if the length scale is greater than 10 nanometer, then we can apply the Navier-Stokes equation with no slip boundary condition. Okay. But if the fluid is gas, then if the Nusselt number is less than 0.001, then we are able to use Navier-Stokes equation with no slip boundary condition, and if the Nusselt number is between 0.001 and 0.1, then we can still use Navier-Stokes boundary condition, but with slip. Okay. So, we will discuss gas flows in a microchannel in case of quiet flow if the fluid is gas and Nusselt number in the range 0.001 to 0.1. Okay. How we can obtain an expression for the velocity profile. So, we talk about quiet flow with slip at walls. Okay. Right. So, we know that for liquids, if the length scale is of the order or greater than 10 nanometer, then we can use Navier-Stokes equation with no slip boundary condition. Okay. Now, for gases, if Nusselt number is less than 0.001, we can use Navier-Stokes equation and no slip boundary condition. If Nusselt number is between 0.001 to 0.1, we can use Navier-Stokes equation with slip boundary condition. Okay. So, we consider here two parallel plates for Couette flow. So, this is one plate, this is another plate, and we say this is the middle line between the plates, and this is let us call it y, this is x. Say this is moving at velocity u by 2 in this direction, and this plate is moving at velocity u by 2 in this direction. So, the relative velocity is u, and so and d is the separation distance. The separation distance between the plate is d. So, this is at d by 2, and this is at minus d by 2. Okay. So, we assume that the velocity profile to be linear. So, linear velocity profile, which you know from the liquid flows. So, if you do that, you can write uy will be a plus by. Okay. So, u at d by 2 is going to be a plus b into d by 2. Okay. That is the upper wall we are talking about, and at the lower wall u minus d by 2 will be equal to a plus b into minus d by 2. Okay. So, and let us say this is the profile nature, and here we say there is a slip velocity of us, and here also there is a slip which is us. So, the plate is moving at u by 2, but the fluid is moving at a lower velocity as compared to the plate, because there is a slip, and so it is moving at u by 2 minus us, right. So, this is u by 2 minus us, and for the bottom plate the fluid is moving at u by 2 in the negative x direction, and the fluid is moving at a lesser velocity us. So, this is going to be minus, because it is going in negative x direction, u by 2 minus us. Okay. So, this is minus u by 2 plus us. Okay. So, now if you look at equation 1 and equation 2, if you solve these two equations, we can see that a equal to 0. We can clearly see that the constant a is going to be 0, and b. So, a and b are two unknowns in these two equations. So, b can be determined as u minus 2 us divided by d into y. Okay. This is going to be b. So, now we can use the Maxwell's slip model. So, using Maxwell's slip model, we know the expression for the slip velocity at the wall, which is a function of the momentum accommodation coefficient lambda and the velocity gradient. Okay. So, we can write that us is equal to 2 minus sigma divided by sigma. Sigma is the momentum accommodation coefficient into lambda into del u over del y at y equal to plus minus d by 2. Okay. So, you can write this as 2 minus sigma over sigma into lambda. Now, from this equation, okay, you know A and B. So, if you substitute in that equation, you have an expression for the velocity profile. So, which is basically B into y, right, B into y, because A is 0. So, sorry, so B is going to be this, B is going to be this. So, this is velocity is By. So, u is going to be u minus 2 us divided by d into y. Okay. So, we can obtain the velocity gradient, which is going to be u minus 2 us divided by d. Okay. So, us is 2 minus sigma over sigma into lambda over d into. So, from this equation you can write us. So, here is us and us. So, you can write us to be u divided by 1 plus 2 minus sigma over sigma into 2 lambda over d. Okay. So, that is the expression for the slip velocity. Okay. Now, you can determine, here you can check as lambda by t tending to 0, your slip velocity us is tending to 0, and which is the case when Nusselt number is very very small. Okay. So, the slip velocity is not existing. Now, from the expression for velocity we can obtain the expression for shear stress. So, shear stress can be written as tau equal to mu del u over del y at y equal to plus minus d by 2. So, you can write this as mu into u minus 2 us divided by d, which is the velocity gradient, and so that can be written as mu into u divided by 1 plus 2 minus sigma over sigma into 2 lambda over d. Okay. So, now, knowing the shear stress, we can calculate the skin friction coefficient. The skin friction coefficient, which is Cf, can be calculated. So, we can write Cf equal to tau. We have an expression for the shear stress tau. So, tau divided by rho u square over 2. Okay. So, you can write this as mu over rho u d into 2 divided by 1 plus 2 minus sigma over sigma into 2 lambda over d. Okay. So, just substitute for u there. Okay. So, from there you can write Cf into Mach number is going to be Mach number over Re, which is Reynolds number, into 2 divided by 1 plus 2 minus nu over nu into 2 into Nusselt number. Okay. So, this expression can be used to predict or to calculate momentum coefficient. Okay. So, if you do an experiment where you can determine the Mach number, Reynolds number, Nusselt number, other parameters, skin friction coefficient, you can use this formula to predict the value of the momentum accommodation coefficient sigma. Okay. So, here if you look at this expression here, if Nusselt number goes to 0, okay, so lambda over d Nusselt number goes to 0, then what we see here? We see that the skin friction coefficient is going to be 2 over Reynolds number, okay, and this is valid for liquid flows in channels where the skin friction coefficient is 2 over the Reynolds number. Okay. Now, if Nusselt number tends to infinity, then we are talking about free molecular regime, right, free molecular regime, and in that case if you put Nusselt number infinity here, okay, you have to rearrange the term so that you can consider the regime Nusselt number tend to infinity. If you do that, you will get Cf will be equal to, so and you have to use Mach number over Reynolds number is equal to 2 over pi k square root into Nusselt number, that we have seen, right, Mach number, Reynolds number and Nusselt number can be related. So, here k is specific heat ratio. So, in that case you can show that Cf is going to be 2 divided by pi k square root into 1 divided by 2 minus sigma over sigma. Okay. So, this is the limit when Nusselt number is very high, Nusselt number is infinite. So, let us stop here.